Hi everybody, we're going to use a FET from University of Colorado Boulder. We would normally do in the computer lab because it uses Java. We can't do it on our iPads. I'm not sure if you can do it on your home computer, so I'm going to work through it in the same order as the worksheet that's attached to this assignment. So let's switch to a different view here called glass layers, since we're using the metaphor of a greenhouse for our atmosphere and how some gases can keep heat in our atmosphere, moderating the average temperature rather than it being very hot when we face the sun and then very cold when we don't face the sun for particular continents. So looking here, we can see that sunlight in the visible spectrum is represented with yellow and heat is represented with red. And over on the bottom left, we have a thermometer. We'll only be concerned with the degrees Fahrenheit. So here we have no greenhouse effect, and we're at -2 degrees Fahrenheit. Notice something about the yellow falling towards Earth. That is the light from the sun. Notice the red, the heat, is only headed upwards. I don't see any coming from the sun down to Earth. That's because the sun, while it does produce heat and energy in the infrared wavelength, that's easily dispersed in the atmosphere on its way from the sun to the Earth. So we do not get most of our heat energy directly in packets from the sun. We get heat energy because the light wavelengths, the light packets of energy, hit solid ground, hit rooftops, vegetation, water, and bounces back in a different wavelength of the infrared of the heat. So our heat is reflected back from the Earth's surface. The heat is not coming directly from above. So I'm going to add glass panes here. Here's with one pane of glass. We'll give it a couple seconds to adjust. My new temperature is in the 60s, the 70s. Now it's time kind of leveling out, maybe, in the low 80s here. I'll add another pane of glass. Notice which photons do pass through the glass and which ones don't. I'm at about 107 degrees Fahrenheit. Now I'm up to 116 degrees Fahrenheit. This is like a car. Even if it's 20 degrees outside and the air temperature is very cold outside, if sun is shining through the windows of your car and your windows are rolled up, that light energy changes to heat energy as it bounces off your dashboard and seats. If your windows are closed, that heat energy is trapped inside the car. Light energy makes it through the glass panes, but not so much heat energy makes it through the glass panes. And here's with the third layer of glass. And we'll watch the temperature rise, and we'll watch the change in number of heat packets that can leave. And we're at about 150, 160 degrees Fahrenheit with 3 layers of glass. Moving on to our next activity, if you follow down on your worksheet, we're going to go to the part about photon absorption. This is a little bit more in the chemistry realm, a little bit in the physics realm. I have a blaster here that can blast heat energy at molecules, or it can blast visible light at molecules. And I'm going to add molecules here. I have methane. CH4 has this shape. I'm going to add carbon dioxide. There's its molecular arrangement, CO2, water molecules, nitrogen or N2 molecules, the majority gas of our atmosphere, and then oxygen molecules, O2, about 22% of our atmosphere. Let's take a look and see what happens when energy in the light, the visible light spectrum, the Roy G. Biv spectrum coming from the sun, is blasted at these molecules. Pretty boring, nothing happening. Let's switch to the infrared. Now heat energy wavelength is hitting these molecules, and notice which ones are doing a little dance. It's a vibration. The technical term is resonate. Different molecules will resonate if heat energy hits them. So I'm going to go through one by one, and you can mark down on your sheet which molecules resonate in the heat when blasted with heat energy or the infrared. So here's methane, CH4, definite resonate. Here's carbon dioxide, definite resonate. Here's water, definitely resonate. Nitrogen gas, N2, nothing. Oxygen gas, nothing. So that resonance means that the heat can get bounced back to Earth. It makes those molecules which resonated the blanket or the greenhouse gas molecules. The ones that don't resonate do not have an impact on greenhouse gas warming, the N2 and the O2. And finally, in our last situation here, about greenhouse effect. In this greenhouse effect simulation, I can pick different time periods, and or I can add amounts of clouds to the situation. So right now, let's go back to the beginning here. Let's do a little. I have an average temperature, it looks like 54 degrees Fahrenheit. I add one cloud, still at about the same temperature. Two clouds, temperature went down a little bit, but still pretty similar. 3, 4, 3 clouds is my max it'll let me have. And I'm at about 54, 55 degrees Fahrenheit, up, bounces down. So it's staying about the same with my clouds. There's a lot of research right now going on with clouds and what do they do in the whole global warming situation. Do they act more as a trap for the heat energy, as we see on this simulation, bouncing the heat back down? Or are they more effective as light blockers, which would result in less heat to reflect back from the Earth into the atmosphere? So maybe it's a wash. Maybe it's a no net effect. Maybe it depends on the thickness of the clouds. That's an area of research right now. Okay, so now I'm going to take you through the questions that are in the second half of your lab, and particularly there is a data table to fill out. So let me reset. I'm going to go to the Ice Age. I'll be reading some of the concentrations to you in case the video quality is not good and you can't read it yourself. Sorry if it's too repetitive. Okay, during the Ice Age, I see that water is an unknown concentration, carbon dioxide 180 parts per million, methane 0.38 parts per million, nitrous oxide or N2O is 0.215 parts per million. They didn't have us test that out in the last part of the simulation, but nitrous oxide is a potent greenhouse gas, and if the nitrogen cycle releases that, usually swamps, bogs, decaying places, then that could be another greenhouse gas to pay more and more attention to. And the Ice Age temperature seems to be about, it's hovering in the high 30s, mid 30s, so maybe you would write down 35 degrees Fahrenheit. Moving on to 1750. We have a little more information that's more direct, not from ice cores, about 1750. In 1750, we have water concentration of 70%, carbon dioxide of 280 parts per million, methane of 0.73 parts per million, N2O 0.27 parts per million. Our temperature is hovering in the high 50s, right down 59 degrees Fahrenheit. Moving to today, this is a bit dated information, maybe 15 years ago. Water 70% relative humidity, which changes day to day, region to region. Carbon dioxide, 388 parts per million, which that is way off for the current amount. We're over 400 parts per million now in 2020. CH4, methane, 1.8 parts per million. Nitrous, 0.317 parts per million. Our average temperature seems to be about 58 degrees Fahrenheit. If I mess around a little bit with this, like if I want to make a prediction and put more greenhouse gas concentration, and I move that slider, I can watch the temperature, and I see the temperature is going up, now more in the middle 60s for the average worldwide temperature. And if I bring it down, greenhouse gas concentration, I can see the temperature gets quite lower. So there's all kind of complicated mathematical models. This one's obviously simplified for our use, but mathematicians, atmospheric chemists, physicists, astronomers, meteorologists, there's lots of scientific research going on in this arena. Thanks for watching. Feel free to rewind whenever you need to for this video.